Ampere circuital law. So the Ampere circuital law states that the line integral of the magnetic field around any closed surface is equal to mu naught times the total current flows through it. So very simple students, when a wire carrying a current I, there will be a magnetic field formed. That created magnetic field can be determined by using this equation. So the line integral of the magnetic field and this elemental length, the dot product of these two things is equal to the permeability of the free space into the total current. So very simple, this is a mathematical expression for Ampere circuital law. So I will recall you, this Ampere circuital law is similar to the Gauss Theorem equation. What is the Gauss Theorem? Gauss Theorem states that the electric flux linked with the any closed surface is 1 by x lambda times the total net charge. So 1 by x lambda times the total net charge. Here mu naught times the total current. So here x lambda naught comes in denominator. Here mu naught comes in the numerator. Instead of charge, total net charge. Here the charge is flowing. That means current. We are representing I. So the electric flux can be represented as a closed integral of E vector dot ds vector. So in the same equation, same mathematical notations we are taken here. Instead of electric field, we are using a magnetic field. For the surface ds, here we are using a elemental length. So the Ampere circuital law is similar to the Gauss theorem. It is easy to remember. So the Ampere circuital law states that it explains the magnetic field of the current carrying conductor in a mathematical form. So this closed loop is called as an Ampere loop. Similar to in Gauss theorem, the imaginary surface is called Gaussian surface. So this closed loop is an geometrical entity. It is not a real one. So proof. What is the proof for current carrying conductor? That is Ampere circuital law. This is a current carrying conductor. It carrying a current I. So there will be a magnetic field. The magnetic loop will be formed. This is an Amperean loop. The magnetic field direction is around this by right hand thumb rule. We are having a right hand thumb rule. This is the direction of the current. So this finger shows this wrapping finger shows the direction of the magnetic field. Thumb shows the direction of the current. So the direction of the magnetic field is in this direction, anti-clockwise direction. So this the magnetic field direction will be moving outwards at any point on the Amperean loop. That we are drawing a vector, the perpendicular or radius of this wire and the loop is r. This length is an elemental length. So by Biot-Savart law, the current carrying straight wire has a magnetic field formula B is equal to mu naught I by 2 pi r. So this equation already we are derived with the help of Biot-Savart law. So B is equal to mu naught by 2 pi r. This small element dl along the circle, the angle between the B vector and dl vector is 0. So by the Ampere circuital law, integral B vector dot dl vector is equal to B dl cos theta. Here the angle is 0 degree. So B dl. So B can be taken outside, integral dl. So the dl is a small length. So for a circular loop, the total length is the circumference of the Amperean loop. So we can take that 2 pi r. Substituting this equation mu naught I by 2 pi r. 2 pi r get cancelled. We get an equation integral B dot dl which is equal to mu naught I. Hence we proved that the Ampere circuital law by using a straight current carrying conductor. This is also an application of Ampere circuital law in the straight current carrying conductor. Very simply we can say that the Ampere circuital law gives the magnetic field mathematical expression for straight current carrying conductor or any current carrying conductor. Magnetic field inside a long straight solenoid. Already we have studied about the solenoid in class 10. A solenoid is a coil of wire whose length is longer than that of the breadth of this coil, radius of this coil. It will be a cylindrical form. Solenoid means an insulated copper wire wound closely in the form of helix. When the battery is connected to the coil of wire, the current is flowing in this direction and it will be comes out in the opposite end. So the magnetic field will be developed as per the Oersted experiment. So the magnetic field pattern is similar to the bar magnet pattern. Hence we can say that solenoid is act as a bar magnet. Yes, here I show the magnetic pattern of the bar magnet. So the magnetic pattern of the bar magnet, north pole to south pole. So this will be similar to the solenoid magnetic field pattern. Hence we are say that solenoid will act as a bar magnet. So for the bar magnet, the polarity cannot be changed. But if you change the polarity, here the polarity will be changed. So how the polarity of the solenoid can be determined? Very simple, students. When the magnetic field is enter into the bar magnet, that is the south pole, and when the magnetic field is come out from the magnet is called as a north pole. Here you can assume that the current entering end is a south pole, magnetic field also entering into the solenoid, and the current come out end is called as a north pole because the magnetic field also coming out. So in the center of the solenoid, the magnetic field is uniform. In the middle, the magnetic field is uniform. But for bar magnet, here the pole strength is maximum in the end. But for the solenoid, the pole strength, that is the strength of the magnetic field, is maximum at the middle. These are all the things now we are going to see with the help of the expression. So the solenoid, we are going to determine that what is the magnetic field inside the solenoid. So this picture shows the solenoid because this dot represents the wire will be coming out. The wire come out from this. This is a coil of wires. Like this it will come. It will come out and get into it. Into mark, cross mark represents the wire go into the plane of the paper, and the dot represents the wire come out from the plane of the paper. This line represents the parallel, that is a magnetic field B is uniform in the middle of the solenoid, center of the solenoid. Here we are representing a parallel line, you know, that parallel line is drawn here. So we are taking a Amperean loop, small, the imaginary Amperean loop A, B, C, D. Okay, so according to Ampere's circuital law, line integral of B vector dot dl vector is equal to mu naught I. So what is the angle between B vector and dl vector? So this is a L, this is a length L or the small elemental length dl. So the magnetic field is B is along in this direction. So the magnetic field and the length are in same direction. For AB, theta is 0 degree. For BC, the magnetic field direction is here and the elemental length is in the perpendicular downward direction. Theta is 90 degree. Again, here the magnetic field is anti-parallel, 180 degree. Here also the theta is 90 degree. Hence we can split the integral into integral of AB, BC, CD and DA. So the AB angle is 0 degree. And the BC angle is 90 degree, and this angle is also 0 or 180 degree, and it is 90 degree. So here I will write the 180 degree also. I will take it as it is a parallel to this one as a 0 degree. But this cos 90 is 0, this cos 90 is 0, this integral, these two will not come. But for the outer loop, this DC, there is no current. If there is a current passes through, then only the magnetic field will be developed. So there is no current passes, there is no wire present, hence this term is also become 0. Finally we get integral BDL, which is equal to integral of A to B BDL cos 0 degree. So since B is equal to 0 for the points outside, because there is no current passes through it. So we can write this integral as a simple way, integral B dl. So B dot dl, so dot is a cos 0 degree 1, so integral B dl. You can take the B outside, integral dl. So dl is a total length of the solenoid. So it is a coil of wire. So the total length of the wire is solenoid is BL. So we can put that it is a 2 pi r for the single loop. For the total loop, the total length is BL. So we can write integral BDL, which is equal to BL. So the total current threading in the loop is ABCD is NLI, because the total length is total length is L, number of turns is N, the current passing through is I. So we can write the total current is NLI. So BL, which is equal to, according to Ampere circuital law, integral BDL mu naught I. So for BDL we can substitute BL. For BDL, we can substitute BL, and for mu naught as it is, for instead of I, we can substitute NLI. So NLI, this L and this L get cancelled. Finally, we get B is equal to mu naught NI. So this is an Ampere circuital law, or the magnetic field of the solenoid, magnetic field inside the solenoid. So from this we come to the conclusion, the magnetic field is maximum in the middle. At the end it is a half of this middle value. So in the middle of the solenoid the magnetic field is maximum, and if you are come to the end the magnetic field is half of its middle value. That is represents in this graph. Similarly, instead of that solenoid, we have the magnetic field due to an toroid also. We are going to see in the next video. So I will show the pages very clearly. First we are seeing that Ampere circuital law. This Ampere circuital law is similar to the Gauss theorem. Okay, then what is the Ampere circuital law? Integral BDL, which is equal to mu naught I. Mu is the permeability of the free space. We are seeing the proof for the Ampere circuital law. Then we are determined that by using Ampere circuital law, we derive the expression for magnetic field inside a solenoid. Very simple equation. Substituting that B value and I value, we get an equation mu naught Ni. Then mu naught Ni is a magnetic field is maximum in the middle of the solenoid. At the ends, the polarity of the solenoid is half of its middle value. What is the middle value? That is the middle magnetic value is maximum, and the polarity magnetic value is half of its middle value. Thank you.